Okay, thanks for the introduction today. I'm going to talk about some of our research related to the fluid simulation. Yeah, title is Fun with Fluids. Okay, the fluids, we see fluids everywhere in our daily life. For example, we see smoke, water, and fire, and so on. So actually, fluids are very familiar with us, and the appearances of and the motions of those fluids are very interesting and attract many people's attention. So it is very natural for us computer graphic researchers to work on the visual simulation of fluid phenomena. And in computer graphics, we often employ a physically based simulation to create realistic animations. So that is, the methods developed in computer graphics are usually based on the numerical solution of Navier-Stokes equations. So shown in this slide. So we are mostly interested in the incompressible Navier-Stokes equations, which are shown in this slide. And we have two partial differential equations. The first one describes the first one is actually the equation of motion, and the second one is the mass conservation condition. Anyway, by solving these these equations numerically, we can obtain the motion or velocity of the fluid, or we can also obtain the pressure field. So we have been working on the fluid simulation so far, and this slide shows some of the research results obtained by using our previous method. We've developed for the simulation of cloud formation, or simulation of smoke, or elastic viscous fluids, and ice melting, and so on. And more recently, many researchers have developed a much more complicated or sophisticated method for simulating complicated different physical phenomena, fluid phenomena, as shown in this slide. So by using these methods, we can create highly realistic, complicated animations of different fluid phenomena. However, we believe that there are still fundamental problems remain with the fluid simulation, which are shown in this slide. The first one is the computational cost. So the fluid simulation is actually very time consuming. So it is not surprising that we need several seconds or tens of seconds or sometimes several minutes for each time step of the simulation. And the second problem is the directability. That is, in some applications, like in entertainment applications, movies or video games, the artists or animators are often requested to produce desired visual effects. However, this is actually difficult for fluid simulation. We have to repeat the simulation with a different parameter setting, and the simulation computation time is usually very long. So this parameter adjustment process is really tedious and time consuming. So we have been focusing on the second problem, and we have developed a set of methods listed in this slide. We developed a method for controlling a simulation, image-based approach, and we have developed a method for editing a fluid simulated data set. Sorry. And recently we developed a guided simulation method. So today in the following, I would like to talk about some of these, and I would like to show you some interesting examples. So let me start with the first one, the controlling the simulation. So controlling the fluid simulation was firstly developed by Trey et al. In 2004. In this case, they use external forces to control the smoke simulation. This one is a example of this method. In this case, the smoke forms the shapes of the letters of SMOKE. So we are inspired by this method, and we wanted to extend this method to the natural phenomena, in our case, clouds. So this slide shows an overview of our system. So in our system, the user first draws a contour line, this pink curve of the desired shape of the clouds. And then our system controls the simulation so that the final shape of the synthetic clouds becomes the same as the shape specified by the user. So we first tried to use the external forces like the method mentioned in the previous slide, but we found that the external forces are not very good for our case. So using external forces often results in unnatural motion and shapes of the cloud. Instead, our method controls a sum of the physical parameters involved in the numerical simulation. Let me talk about some of the details of this method. Firstly, I would like to talk about an overview of the cloud formation process in the real world using this slide. So when there are no clouds in the sky, the ground is heated by the sun. And then the air near the ground starts to move upward due to thermal buoyancy force. And as these air parcels move upward, their temperature decreases due to a phenomenon called adiabatic expansion. And finally, at a certain altitude, a phenomenon called phase transition occurs. That is, water vapor becomes water droplets. And these water droplets are perceived as clouds. And furthermore, when the phase transition occurs, a so-called latent heat is generated. And this latent heat creates additional buoyancy force. And this additional buoyancy force promotes further cloud growth into higher regions. So these are the phenomena involved in the cloud formation. So these phenomena can be described by these 6 partial differential equations. So first two are actually the Navier-Stokes equations, and the third one is the buoyancy force, and the fourth one represents the temperature of the atmosphere, and the last two are related to the phase transition between the water vapor and the water droplets. So by solving these equations numerically, we can obtain this kind of animation. So in this case, we try to create a kind of realistic animation of the cumulonimbus formation. So we repeat the simulation many times to create this animation to adjust the parameters in the simulation. So it is very time consuming to create this kind of animation. So we want to address this problem. So through a number of experiments, we found that the shape of the clouds can be controlled by adjusting this one, the amount of latent heat. So as I mentioned in the previous slide, the latent heat promotes further cloud growth into higher regions, so we can adjust the height of the clouds by controlling the amount of latent heat. However, the latent heat is not generated unless the phase transition occurs. So therefore, additionally, we decided to control the phase transition process. Particularly, we actually add certain amount of vapor to promote the phase transition. Anyway, we developed 2 controllers for these 2 variables, and by using these controllers, we can control the generation of clouds and vertical cloud development. And the one important feature of this method is that we do not use external forces. So we call our method is a kind of implicit control. So this implicit control tries to preserve the dynamics of the cloud formation as natural as possible. So we believe that this method can create realistic animation of the cloud formation process. Okay, now let me show you some results. But first, I would like to show you a comparison between the results using the external force and the results using our method. So let's see first this one, results using the external force. So this pink curve indicates the target shape. So although the target shape is formed, but the motion of the clouds is not realistic very much. So let's see then our method. In this case, the clouds naturally grows, and the shape, the clouds finally forms the tight shape. Okay, now let me show you some more practical examples. In this case, we try to generate typical cloud shapes that are often observed on a hot summer day, like this one. This is a target shape specified by the user. And then now the simulation is controlled. And finally, the target shape of the clouds is formed. Next one, in this case, we use a photograph to control the simulation. So this is the photograph of real clouds, and we manually extract the contour line of these clouds and use the extracted contour line to control the simulation. This is extracted contour line. So here is the controlled simulation. So if you compare the shapes of the synthetic clouds and the real clouds, the overall shape is similar. So I think we can, this method can be considered as a kind of image-based modeling of the clouds using the simulation. The last one, in this case, we try to create kind of unnatural clouds, in this case, skull-shaped clouds, by creating two holes inside the clouds. This is the target shape specified by the user. This is a holes. And in this example, we actually use some external forces around these holes in order to prevent the clouds coming into the inside these holes. However, overall shapes and motion of the clouds are kind of realistic because our method tries to simulate the cloud formation process as naturally as possible. Okay, that's the first one. Okay, next one, I'd like to, let me skip the second one. If you are interested, I can show you later. So let me ask after the talk. So let's move on to this one, editing approach. So in this case, fluid simulation is expensive. So in this approach, we wanted to reuse the simulated data set for different scenes. By modifying the simulating data set. So this picture shows an example of this approach. So we see 3 streaks of the smoke rising from chimneys, 3 chimneys. So among these, the one is simulated by solving the Navier-Stokes equation, and the other 2 are generated by editing the simulated one. And the answer is like this. The leftmost one is actually simulated with the time-consuming simulation, and the other 2 are generated by deforming the leftmost one. So this looks good, but the natural question is that, so are these deformed smoke realistic or not? So however, this question is difficult to answer because we have no clear definition of the realism of the synthetic smoke. So instead, we replace this question like this one. So are these physically reasonable or not? This question can be answerable because we have some equations for computing the motion. So in this particular case, we designed the deformation method so that this condition, mass preservation condition, is satisfied. So our editing approach is based on this concept. And recently, we have developed two approaches based on the idea described in the previous section. The first one is a flow interpolation, and the second one is a style transfer. So I would like to talk about the first one only today. The first one is actually an interpolation technique, and the second one is a kind of extension of the texture synthesis to the velocity field. Yeah, let's move on to the first one, this one. So this one is mainly done by this person, Shuhei Sato, who graduated from my laboratory, and yeah, he got PhD from our laboratory, and he is now working for a private university in Tokyo. Anyway, so what we wanted to do with this research is the cut and paste operation for the fluid flow. So let's see an example shown here. So in this case, this one is generated by the numerical simulation. We see there is a sphere, and smoke interacts with this sphere. So what we want to do, for example, is that we want to duplicate this sphere region into this region by selecting this region and copy the region into this one. And then our method can achieve this result. And here is the animation. And in other case, sometimes we want to remove the sphere after the simulation. This can be possible by our method by selecting this region and copy it into this region. And here is the result. And this is the animation. Okay, the cut and paste operation is actually common in other media, like image or text, as shown in the slide. And our research in this case is inspired by this method, the Poisson image editing. This is one of the famous methods in computer graphics, and this method can naturally combine the images as shown in this picture. So we first we wanted to we tried this method to for the velocity field obtained by the fluid simulation. So let's see this example. We have two data sets. One is the smoke interacting with a kind of sphere, and the other one is the more taller smoke. And we want to put this one into this region. When using the Poisson image editing technique, we should solve this minimization problem. And this technique can modify the velocity field velocity inside the copied region, this region, to make the smooth transition between this region and the other regions. So, however, we found that this approach did not work well. So let me show you an example. So this one, in this case, we want to copy this region into this region, and although it is not displayed, there is a obstacle in this region, and this is the result using the Poisson image editing. So let's see the animation. Yeah, you see the result is not realistic very much. It's not. The result is very different from what we expect. So the Poisson image editing technique modifies the velocity field inside the copied region. So the resulting velocity field is too blurry, and the results are not very good. So our solution is very simple. So instead of modifying the velocity inside the copied region, we assume that the boundary region indicated by this white region, and we modify the velocity inside the boundary region only by solving this kind of slightly different minimization problem. let me show you the same example, but with our method. Yeah, in this case, we can obtain the kind of expected and convincing result. Okay, let me talk some of the details of our method. So this is the minimization problem we want to solve. And after through the several mathematical operations, we can obtain this equation, this formulation. We have two terms on the right. And the first term tries to minimize the vorticity, and the second term tries to minimize the divergence. The second term is good because this term corresponds to the divergence-free condition. So by minimizing this term, we can preserve the mass conservation condition. But the first term is not very good. So if we minimize the vorticity, the resulting flow becomes too smooth. So instead, we heuristically replace this term into this one. The difference, we want to minimize the difference of the vorticity to preserve the vorticity. So in this term, U hat represents that the advected version of the velocity that is computed at the previous time steps. So the first term, so therefore the first term tries to preserve the vorticity throughout the animation. So then by using some mathematical operation again, we can finally reach this kind of equation. This one is actually we need to solve. This equation is actually called a vector Poisson equation. So from this equation, we obtain three sets of scalar Poisson equations for each of the XYZ components. So we solve these equations using a conjugate gradient method. Okay, now let me show you some examples using this method. So firstly, this one shows the computation time. And if you look at this column indicates that the computation time for the optimization process in our method. And this column shows the computation time for the full simulation. So if you compare these two, our method is much faster than the full simulation. And particularly in this example, the computation time is 420 times faster than the full simulation. Okay, let me show you some examples. This one is the same one as the one shown in the beginning. So let me skip this one. I'll skip this one. So next one, this one, in this case, we have two velocity fields, this one and this one. And in this case, we want to copy this region into this region. So let's see the animation. So these are the input velocity fields. And here is the result. You can see that our method can successfully combine the flows with different turbulence. And the next one, in this case, we have a single input velocity field, this one, and we want to make the smoke taller by inserting the interpolation regions horizontally, like as shown in this figure. Let's see the result. And also we can create wider smoke in a similar way, like this one. Yeah, this is a similar example, but in this case, we want to make the tornado, creates the taller tornado. And this is the final example in this method, by this method. In this case, we want to make a large-scale sandstorm animation, but the simulation of the large-scale sandstorm simulation is very time-consuming. So we split the simulation into two, this one and this one. Let's see. And then we arrange these two simulated data set like this way. This one is placed at this place and this place, and this one is put in the center. And when we interpolate the velocity field at the boundary regions, this one, to make the smooth transition, and resulting animation is like this. Okay. Okay, let's go back to the main slide. Okay, next, I'd like to talk about this one, guided simulation. This is the our recent research result. So the guided simulation, yes, guided simulation was firstly proposed in these two papers. The same first author, I think that Nielsen invented this guided simulation approach. Anyway, the guided simulation framework, the user first prepares a kind of low resolution velocity field using the low resolution simulation. Since the low resolution simulation can be run in real time, so the user can design the flow interactively using the low resolution simulator. And the guided simulator uses the low resolution velocity field, this one and this one, as input, and synthesizes high resolution small scale details as shown in this picture. So if you compare this one and this one, and then the overall motion looks similar, but the high resolution details are successfully generated. So this method is very useful, and it is very convenient, particularly for the production environment. However, the problem is the computational cost. So this method works on the velocity space. That is, when the input velocity is specified, it is then upsampled, and the method solves a certain optimization problem to determine the velocity and pressure fields for high resolution grid. So therefore, the problem size becomes very large, so the computation is very expensive. Recently, these authors developed a much more efficient method. This method works on the frequency space, and that is, the input velocity field is transformed into frequency space by using the first Fourier transform, and then the high frequency details are added in the frequency space. So this method does not solve any optimization problem. So the computation is much more faster than the previous optimization-based method. And the implementation is very easy. So however, we found that this method does not work for non-physical inputs. So this is an example of such non-physical input. In this case, we do not use a kind of fluid simulation to prepare the input low resolution velocity field. In this case, we manually create a very simple velocity field like this one to make the smoke form the arch shape as shown here. The previous method does not work well for this type of non-physical input, but our method can produce kind of convincing results. So let me show you some comparison. So this is the input velocity field. This is a kind of very simple velocity field. So here is our result. Yeah, our method can produce a kind of realistic results. But if we use frequency domain method, this is a result. So the method does not produce actually the method completely fails to produce convincing results. So this is a result obtained by using the previous or original optimization-based method. This looks good, but if you compare this one with our method, let me show you a side-by-side comparison here. So I think our method seems, the result obtained by our method looks more realistic. Okay, now let me talk about the details of this method. So the previous method works on the velocity field or the frequency space, but our method works on the stream function space. So stream function is actually computed from the velocity field. In our method, use the input velocity field by solving a Poisson equation. For 2D case, the stream function is actually a scalar function. And once we obtain a stream function like this one, then we can convert this stream function into the velocity field by applying a curl operator to the stream function. And the one important thing here is that by computing the velocity field computed from the stream function is completely divergence-free. So the mass conservation condition is completely satisfied. So our method works on this stream function. So after computing the stream function from the input velocity field, our method solves modified optimization problem, and we obtain the high resolution guided stream function. And then we apply the curl operator to the guided stream function to obtain the guided velocity field. Again, I would like to mention that this velocity field is completely divergence-free. So I think this is very important to create realistic results. So our method, we formulate our optimization problem to reduce the problem size. And as I shown in the previous slide, our method is applicable to the non-physical inputs. Okay, now let me talk more about the optimization process. So this is the formulation used in the previous original optimization-based method. So let's see this formulation in more detail. This term is the input velocity field, a kind of low resolution velocity field. And then this one is the advocated version of the guided high resolution velocity field computed at the previous time step. So the previous method computes the velocity and the pressure field for high resolution grid. So therefore, the matrix size, the resulting matrix size becomes very huge. So the computational cost is expensive. So also the previous method needs to take into account this condition as a constraint. So we replace this formulation with this one. So if we compare this one and this one, so actually we replace this term into this term. We use the stream function here. And our method determines the stream function. And as I mentioned in the previous slide, by computing the velocity field from the stream function, the resulting velocity field is completely divergence-free. So we do not need to take into account this condition anymore. So however, this formulation does not reduce the problem size very much, because the stream function in 3D case is called a vector potential, which is a kind of vector function, and the dimension of the vector potential is the same as the velocity field. So the problem size is not reduced very much. So in order to reduce the problem size, we heuristically introduce a scaling function W here. Scaling function is a scalar function. And we use existing or pre-computed stream function, this one. So the scaling function is a scalar function, so we can reduce the problem size. And for the stream function, we use the stream function computed from the input velocity field. So furthermore, we introduced an additional term, this one, kind of regularization term. So this term works as a control to allow the user to control the effect of the guiding, and alpha is a control parameter. By choosing larger value for this alpha, the resulting guided velocity field becomes similar to the input velocity. Okay, now let me show you some examples. So this one is uses a kind of non-physical input. In this case, we want to make the smoke form the circular shape. This one, this is the input velocity field. And here is our result. A realistic motion is obtained. And if we use the frequency domain method, again, the method does not work well. And this is the side-by-side comparison. Next one, in this case, this is an example of a branched flow. Again, this is a non-physical input. This is the input velocity field. Then this is our result. And the frequency domain method does not work. Yeah, this is side-by-side comparison. Next one, this one, I think this one is a kind of interesting. In this case, we use the same input velocity field as the one shown in the previous slide. This one to make the smoke form the arch shape. But in this case, we put the obstacle, in this case a sphere, in the center. And during the optimization, we take into account the effect of the obstacle. Then we can obtain this kind of realistic results. This one is a more practical example. In this case, we try to generate whirlwind smoke. Yeah, and the input velocity field is also generated manually by ourselves. Okay, finally, this one is kind of actually a comparison using the physically based input. That is, we use a numerical simulation, fluid simulator to prepare this input velocity field, and we compare our results with the frequency domain method. These two are generated by using our method, and these two are generated by the frequency domain method. Let's see. So when using our method, the results changes depending on the control parameter alpha. If we choose larger alpha, the resulting motion of the smoke becomes similar to the input smoke. And if you choose smaller value, then the results become slightly different from this one. Yeah, and for the frequency domain method, this method also has a single parameter that is a cutoff frequency shown here. So we need to choose appropriate parameter for this cutoff frequency. If we choose inappropriate parameter, in this case 1/4, the result is not realistic very much. But if we choose appropriate parameter, in this case 1/12, then the result seems the best among these four. So I think if we prepare the input velocity field by the numerical simulation, the best choice may be the frequency domain method. But if we use a non-physical input our method may be better. Okay, and that's all for the contents. Let me conclude the presentation. So we have proposed a method for improving the directability by, we have developed a method for controlling the simulation. And in this talk, I didn't show any results, but we have developed a method for modeling fluid volume from a single video. And we also developed a method for reusing the existing data set. And as for the future work, we want to extend these methods to different natural phenomena, like clouds or fire or something like that. And we are also interested in the stylization of the simulated synthetic fluid phenomena. Okay, that's it. Thank you for your attention.
Okay, thank you for Professor Dobashi for the talk. Okay, any questions? Seems that there's no question, right, from the audiences. So if there's no question, so I may ask some. My first question is that for the fluid cut and paste. So yes. If I am not wrong, the Poisson equation is actually solved at the boundary, not in the whole region, right?
Right.
Then why solving the Poisson equation at the boundary can make the pasting more realistic than solving the solving the Poisson equation at the whole region? So I just want to know the reason behind.
I see. I think that if we solve the Poisson equation inside the copied region, the velocity field becomes how to say kind of all inside the boundaries, the velocity field, all the velocity is modified and kind of smoothed out, so the resulting flow becomes something like this. I think that's the reason.
Okay, so but there should be some thickness of the boundary to be determined, right? So for solving the Poisson equation, right?
Should be what?
There are some thickness. I mean,
yes,
so
exactly.
yeah. So how can the thickness to be determined? So is this an empirical value or some kind of guidance on the determination of the thickness?
Yeah, it's actually we have no. It is actually determined experimentally. We have no clear solution to determine the size of the boundary region.
I see. So that means that for different applications or different scenarios, this value should be chosen empirically according to that kind of a scenario. Huh?
Yes, exactly.
Okay, thank you. And my second question is about the last talk about the fluid guiding. So according to your formulation, there is a weight W in the minimization process, right? So my question is that the first is that how this weight can be determined?
Yes, actually, this is the unknown variable. We optimize this variable to minimize this energy function.
I see. This is to be determined, to be solved, right?
Exactly.
Okay, I see. And then you compared your technique with a frequency domain method. So I just wonder why frequency domain method can fail for many cases.
Yeah, that's a good question. Actually, we try to find the exact reason, but actually we don't know why. Maybe the non-physical for non-physical input like this one. Maybe the frequency in frequency space there should be some discontinuous frequency. That may be the reason. We need to investigate more.
Okay. Thank you. Okay, I have no questions.